So I'm going to change gears a little bit this afternoon. This will be I think quite a different direction from the quite a different direction from this morning and also from yesterday's lectures. But I hope you will find it interesting. And I don't have quite as many slides as the morning, so I hope you'll feel free to ask questions as we go, and hopefully we'll have lots of time for discussion as well. Okay, so biomass energy with carbon capture and storage. So this I showed this morning, and the talk this afternoon is primarily on the second point here, that the opportunity for taking CO2 out of the atmosphere through the use of biomass for energy. And it's, as you will see from some of what I will talk about, it's one of the ideas that is most talked about for reducing the concentration of CO2 in the atmosphere. So here's an outline of what I'm going to talk about. Climate change risks and the carbon emissions budget, which these are terms that you probably have heard about, but I'll explain each one. And the 2 degrees C challenge. This is the agreement in the Paris climate agreement that we try to keep the temperature rise below 2 degrees C and even maybe below 1.5 degrees C. And the question to ask is, do we really need to capture CO2 from or take it out of the atmosphere in the form of negative emissions? And I'll make some arguments that suggest that this is going to be very important. And then I'll talk about some of the technologies that are under development for doing negative emissions, including, importantly, the storage of CO2 below ground. And then that'll set up the discussion of bioenergy with CCS, specific technologies and economics for that. And then I'll finish with some final thoughts. So who knows what this is? Does anybody know where this is or what it is? Somebody said? Australia. This is the Great Barrier Reef, which is bleaching. The coral is bleaching, and this is happening in other parts of the world as well. And the analysis that has been done says that this event was highly unlikely without climate change. So climate change is already having impacts on ecosystems in different parts of the world. And this is a diagram from the IPCC, the Intergovernmental Panel on Climate Change, their most recent report that shows the level of risk in different aspects of our global system as a function of the temperature rise that happens with global warming. And the risk is very high, to high, moderate, or to none. And so these are unique ecosystems, such as dying coral reefs. And we are already at about 1 degree C of warming, so we are already subjected to some risk, added risk from climate change. And at 2 degrees C, which is the target in the Paris Agreement, we see that there will be continuing impacts, but those are judged by the science community to be maybe tolerable. There's of course a wide range of uncertainty around what the impacts will be, but the general sense is that 2 degrees we might still be okay. So those are the risks, and it's quite a simple matter actually to determine how much CO2 we have left that we can emit into the atmosphere before we will reach a 2 degree C warming. And the reason is this is the warming, and this is the cumulative emissions of CO2 over all of the time we've been emitting CO2 since the beginning of the Industrial Revolution. And what you see is that the concentration in the atmosphere it goes up. The temperature goes up linearly with the cumulative emissions of CO2. So this is what the cumulative emissions have been up until maybe a decade ago, and that corresponds to a 1 degree temperature increase. And as we continue to increase emissions, we continue to climb up this line, and it's more or less a linear process. And these represent the concentrations of CO2 that correspond to warming. So 2 degrees C is around 450 to 500 ppm of CO2 in the atmosphere. And the reason this works so nicely is that we know that about half of the CO2 that we emit into the atmosphere stays there essentially forever, long in terms of human timescales. And so from this, we can calculate quite easily what the budget is that we have left in terms of CO2 that we can put into the atmosphere before we will be unavoidably committed to 2 degrees C. And it's quite, again, there's uncertainty around it, but the budget that was left to spend starting from 2016 was somewhere between 600 and 1,200 gigatons of CO2. That's the cumulative amount that we have left to emit. Okay? So to put that number in perspective a little bit, yes, question?
Yeah, does this account for the saturation of CO2 in the atmosphere, where it's not going to keep absorbing more because it's already absorbing all of the IR radiation?
I assume it does.
Okay.
Yeah, but I'm not a climate science expert, but I think these are climate models that are used, and they are supposed to have the physics of that in the models. So.
Right. Okay. Cool. Thanks.
Yep. Other questions? Okay. Where? Oh, here.
I was just wondering, the range that we are allowed to spend is quite big, so it's from 600 to double the amount. So what exactly is the number? Is it 600 or 1,200?
So keep the mic and let me ask you a question. Why do you say it's big?
Because it's... you mean the difference?
You
because
said the number is big. Do you mean the difference is big?
Yeah, the difference is big. Between 600 and double the amount. I mean, it's a huge difference.
Okay.
To me, at least.
Okay. So I would say you have to look at numbers relative that gives them perspective on this, which I'll do in the next slide. So even if, let me just go to the next slide. So this is the remaining budget that we have left for a 2 degree C. I said 600 to 1,200. I picked a number in the middle, about 990 here. This is, again, for different scenarios of carbon emissions, okay? So the trajectory that we're on currently is more like this, okay? So to me, 6,200 is a much bigger number than 1,000 or 600 or 1,200. That's what I was asking about. Why do you say it's big? So, yeah. But even the more important comparison is with these numbers over here. This is the amount of carbon that's still remaining in fossil fuels that we know is in the ground and can be extracted economically. So there's oil, there's natural gas, and there's coal. So if we use all of these fossil fuels that we already know are there and know how to extract, we would be up in this range. And in fact, the amount of fossil resources which we think are out there but we haven't verified is 3 to 13 times this level. So we have a question here.
Hello, my name is Alex from Belgium. I just wanted to know what is the actual rate of emission of CO2 annual? And if you
it's about 40 gigatons per year right now. Right. So 600, if we have a 600 gigaton limit, that's about 15 years at the current rate if we don't get faster than that. So the point here is that we have a lot of carbon in fossil fuels that we're not going to be able to use if we want to stay below any of these concentrations of CO2. And so the question is, how fast can the world shut off the fossil fuels? And so far it hasn't been shutting it off very, very rapidly. And the question is, will it shut off rapidly enough to meet the 2 degrees C? And if it doesn't, then you need to take CO2 out of the atmosphere. And that's where the idea of negative emissions comes in. So most of the, as I'll show you, most of the scenarios for 2 degrees C assume that that you won't be able to slow fossil fuel use fast enough in order to avoid that. So you have to end up taking CO2 out of the atmosphere. So let's just do a simple calculation here of how many people have heard of the Kaya identity? The Kaya identity. Okay, a few of you. So this is just a very simple relationship that says the amount of CO2 that's emitted per year globally or nationally or at any level is the number of people doing the emitting, the GDP per person per year for the region, the energy use per GDP, so this is sort of an energy efficiency of the economy, and then the carbon intensity of the energy that we're using. And you can use this relationship and project the population, so using the United Nations population projections of maybe 10 billion people by 2050 and 11 by 2100. GDP per capita, if that grows at the recent historical rate, about 1.5% per year, and the energy efficiency of the economy decreases at, let's assume, twice the global rate because we want to try to do something about the carbon problem. You can do a calculation of what the carbon content of the energy that we're using has to be over time. And so what this shows is the ratio of the carbon content, CO2 per energy unit today, and how that needs to decrease over time. And so in 40 years' time, our entire energy system would need to be 0 carbon per unit of energy if we want to decarbonize along the 2-degree pathway, but without any negative emissions. Okay, so that's a line. Again, we need to compare that against something to see what it means. So this is over the same last 70 years in the United States, this has been the rate at which the energy content, the carbon content of our energy has been changing. So it's been going down slowly. So for example, when coal, you can see this drop here. This is largely because of natural gas coming in and displacing coal, all right? But it's nowhere near this kind of a rate. But of course, we haven't had a driver like climate change to drive this. Another example is France. This had a very rapid, so this was over from 1965 to 2013, a very rapid drop in the carbon intensity of the energy in France. Does anybody know why this happened? Nuclear, everybody knows, okay. So they built nuclear plants because of the oil crisis, and it was a crisis that drove them. And so for about 10 years, there was a very rapid decline in the carbon intensity, but then once the crisis went away, then they sort of leveled off. So to decarbonize globally, we'd have to more or less follow the French model, but do that continuously for 40 years. So that seems like quite a challenge to me. And there is a motivation for those of us who worry about climate change, but a lot of the world is not worried about climate change as their primary concern. So because without negative emissions, that decline rate is so rapid, most of the scenarios. So this is showing the annual emissions of CO2 over time for different scenarios that lead to different levels of warming by the end of the century. So this is more or less the 2 degrees C scenario, and you see that emissions peak by 2025 or 2030 and decline and actually go negative here. And all of these lines are different climate models running the same target of temperature, and some of them have different assumptions, so some go much more negative, some go less negative. But generally, most of them fall below zeros, which means negative emissions. Okay. So this is a average version of many scenarios showing, and I think this was actual emissions are here. The scenarios were put together around 2010, so they don't quite match up here. But so actual emissions were up here in 2015. This is the median scenario for many different climate models. So there's an equal number higher that come in higher than this, and an equal number that come in lower than this. And what's interesting, so this is the net emissions globally, goes negative around 2070. But in fact, the model is calling for actual negative emissions to offset these positive emissions here, starting around 2030. Okay, does that make sense to everybody? All right. So even though emissions need to be negative at some point later in the century, the models really want negative emissions starting very soon. And then the other point to make here is that, and Suwani has talked about the Brazilian commitments for intended nationally determined contributions. These are the commitments that countries have made in the Paris Agreement that they intend to reduce their emissions by 2030. If you put those together, the emissions trajectory globally is still climbing. Okay, so you have that much more emissions, CO2 in the atmosphere that you have to deal with. So, so my suggestion is that if we want to avoid, if we want to have any chance of staying close to 2 degrees, we're going to need negative emissions. And this is so there's a lot of work going on around the world to try to understand what technologies are, what the sustainability factors are, what the economics are, and it's split up basically into 2 types of systems: biological systems and engineered systems, or sometimes called chemical systems. So on the biological side, you can grow trees. And if we take land and grow trees, we're going to take carbon out of the atmosphere. But we'll have to leave the trees there, and the land won't be available for other purposes at that point. Agriculture, there's a number of things that we can do in agriculture, such as no-till cultivation, which will both reduce the emissions, but also help absorb carbon into the soil. So I showed this morning abandoned cropland. If we grow perennial crops on that, they put roots down and take carbon and put it in the soil. So that's another way to get negative emissions. I'm going to skip this one for a minute because that's the one I'm going to talk about more. But we come over here to engineered systems. So there's a couple here, direct air capture. So there's CO2 in the air, and you can react that CO2 chemically and have it taken out of the atmosphere, and then put into a solvent, and then you release the CO2 from the solvent, and now you have a concentrated stream of CO2 which you have to store somewhere. That's called direct air capture, and we actually know how to do all of these things at some level technically, but the economics is what's quite challenging. There's also enhanced mineral weathering. So there are certain types of rocks that will react with CO2, like calcium oxide and others, and you can basically create mountains of rocks that store CO2. That's a pretty challenging task as well, since you're going to have literally mountains of carbonate rocks. The option in the middle here is bioenergy with CCS. So we're using both biological and chemical processes here. So we're going to grow biomass, and then we're going to use it for energy, either convert it to biofuels or convert it to electricity. And in the process, there'll be some CO2 that's released in the conversion, and we'll capture that chemically, and then we'll store it underground or in other ways that we can store it. So it's a little bit hard to see, but this is sort of a summary of the characteristics of the biological processes and of the engineered processes. So these are less costly, these are more costly. These are closer to deployment. We know how to grow trees, for example. These need a little bit more, or a lot more in some cases, research and development. These are more vulnerable to reversal. So if we grow trees and somebody cuts them down and burns them, the CO2 is right back in the atmosphere. These are less vulnerable to reversal. These have environmental co-benefits. For example, in agriculture, you can improve the productivity of the soil by putting carbon into it. So you get the carbon benefit and the co-benefit of improved productivity. This one on this side, since we're developing new technology, you have the chance of becoming a leader in a new technology, and there may be new industries created which would create employment benefits. So there's sort of trade-offs on both of these, and biomass energy with carbon capture and storage sort of falls in the middle on all of these factors. So this is a very high-level overview of all of these different measures and what the expected cost of CO2 removal is, dollars per ton of CO2 taken out of the atmosphere. And this is the size of the potential CO2 that we can remove. All right. So, for example, reforestation is considered to be one of the less expensive options. But it's also somewhat limited in terms of the total amount of CO2 that we can remove because of land use, land constraints, right? Agricultural soils and best management practices for agriculture. These have, again, these are relatively inexpensive, but also somewhat limited in total potential. BECCS is, so then let's go to the engineered system, accelerated weathering, which is the carbonate rocks, or direct air capture. These, direct air capture in particular, it has a large potential, but the expectation right now, or what we understand about it right now, is it's quite expensive. Ocean fertilization, I'm not going to talk too much about this, as Charlie mentioned it in his talk, where you could store, you fertilize the ocean with a nutrient like iron that's the limiting nutrient for the growth of algae or plankton, and that promotes the growth, which takes CO2 out of the atmosphere, and then the carbon sinks to the bottom of the ocean. That's generally, I think, and Charlie can talk more about this, is that it's generally considered the risks to the ocean ecosystem are too serious to pursue that route. But there were estimates made at one point of what the cost and potential would be for that. Biomass energy with CO2 capture and storage, it falls in a relatively low cost range and a relatively high potential for cumulative CO2 storage. So that makes it an interesting one. If we're going to go after negative emissions, it makes it an interesting one. But again, all of the issues of sustainability that we've been talking about the last 2 days, they all apply here, plus some additional ones because we're storing CO2 below ground. This is, so this is, go back. This is basically this dot here. A little bit more detail on different measures that you can take, restoring degraded lands, biochar application. I haven't talked too much about biochar, but Charlie talked about it yesterday. That's where you do a pyrolyzed biomass, and the solid fraction that's left over is essentially carbon that can be, it's solid form that can be buried for storage or put into the soil to increase the productivity of the soil and stored that way. So there are a number of different measures, and they have different areas across which you can adopt these measures, and the reduction per hectare utilized changes. That you have some very high potential measures and lower ones here. And yeah, this came out of a paper in Nature called Climate Smart Soils, if you're interested in digging into that. The total technical potential here was estimated, if you did all of these measures, somewhere between 4 and 8 gigatons per year. So that's about, 10 to 20% of our current emissions, annual emissions. But again, these things take time and a lot of activity around the land. Okay, so if we don't store carbon in the soil, what are the other options? If we employ BECCS, for example, we now have a concentrated stream of CO2 that we need to put somewhere, and there's different ways of doing that. Biologically, again, we can grow things, but we're limited in how much land we have and how much time it takes. We have the mineral weathering that I mentioned. Again, this would involve lots of mining, big reactors, and probably impractical volumes of rocks. Ocean storage, where you can inject CO2 directly, but that again has a lot of ecosystem concerns. And then the last one, which is getting most of the attention today, is underground geologic storage. So I'm going to talk about that a little bit. Questions, comments?
My name is Kelly from Brazil. Will you talk more about the mineral option? Is it an industrial process that is needed, or how is it done?
I'm not going to talk too much about it, but it is an industrial process. Well, there's different ways to do it. Some of you may have heard some experiments in Iceland recently where CO2 is injected directly into rocks that have the properties that they absorb CO2 very rapidly. So there are some unique geologies where that will work, but the more general one is where you mine rocks and then you put it through an industrial process to react with the CO2. So it's a lot of mining and a lot of industrial processing. Yeah.
I think there is an expression that the cheapest energy is the one that you don't consume, you don't spend. My doubt is whether you have made any economic calculation whether the cheapest CO2 sequestration is the CO2 that's not emitted, or the oil or gas that is not brought up from underground.
Your question was whether I have made any calculations on that. Yeah, I completely agree with you that the cheapest way to avoid emissions is to get more efficient in the way we use energy, to reduce the amount of energy we use, right? To leave the carbon underground. Right, that's effectively, so if you don't need to use the oil, don't use it, right? Yeah. Right. But so energy efficiency is one thing, but substitution of the energy is different, right? So to substitute a unit of oil with something else like a biofuel is more expensive than not using that oil and having a more efficient car, for example, that uses less oil.
What you need to compare is the unit of oil, the barrel of oil extracted from the ground, compared to what would cost afterwards to capture that CO2 with one of these processes. So if you add up that cost, then it might be competitive with the biofuel that seemingly is more expensive, but in the biofuel process, there is the CO capture already calculated within. Yeah?
Yes, you're correct. But so the assumption behind what you just said is that not emitting CO2 has some value.
Sure, it has. It should have. Actually, it has because we have a carbon trading mechanism already in place.
When you say we, who do you?
The United States has a market for this, and there is the Kyoto Protocol, and I think we value the carbon emissions in terms of credits. No?
Have you been following who's the president of the United States right now? California has a market, and the Northeast has a market, and the European Union has a market. So there is a value, but the value is way too low to have an impact that's needed like this. But I basically agree with you that if carbon is valued high enough, then that's the calculation that needs to be done. Yeah. Okay. Other questions? Okay. So let me talk about CO2 storage, because this is a somewhat controversial technology with a lot of people, and particularly people who are purists, I would say, in that it has to be all renewables to solve our problems, because this has the sort of, sometimes people call this geoengineering, because we're changing things quite dramatically. But if we're going to not be able to stop fossil fuel use for whatever reason, political or otherwise, it may be something that we have to do. So I think it's important to understand what the consequences might be and what the cost might be of doing something like this. So the IPCC has done a special report on this quite a while ago now, and their assessment, which is quite preliminary, but I think there's quite widespread agreement since then on this, is that there's a lot of capacity below the surface of the Earth to store CO2. That's where we've taken the carbon from originally as fossil fuels, so there's room to put it back down under. Oops. There's also, so the estimate here was about 2,000 gigatons of CO2, and fossil fuel emissions are about 40, so that's about 50 years of, if we captured all the CO2 from fossil fuel use, that's about 50 years that we could put it away, which hopefully will give us time to find something better, better solution. The concern about the CO2 staying below is one that a lot of people have, and again, you have to look very carefully at where it's going, but there is quite a high degree of confidence that places can be found below ground to keep it there for a long period of time. And then the other issue is you have to have pipelines of CO2 to take it around to places where you put it below ground. And there are lots of those CO2 pipelines operating today. I'll show you some in the US. And so that's not considered a very risky thing. So there's different places underground where you can put CO2 and different ways of doing it, and this is sort of a summary of the different ways. So the first one is enhanced oil recovery, which means you, in an oil well that's been producing for a while, as the oil production starts to decline, if you inject CO2, you can push more oil out. And at the same time, the CO2 is going to remain there when you finish the oil well. You close it off and the CO2 stays down below. So that's something where oil companies today are actually paying for CO2 to use for enhanced oil recovery, and there's recently passed in the United States some incentives for doing this as a way of CO2 capture. So that's something that's essentially economic today. You get paid for the CO2, right? You have oil and gas wells that have stopped producing altogether, and you can inject CO2 into those and then seal them off. That's another place to put it. And those formations kept the oil and gas in place for millions of years, so the expectation is that if you close the holes where you took the gas and oil out of, then you'll be able to seal that back up, right? But the problem with that is that there are not that many places where you have old oil and gas wells that you can use. Also, coal seams that are not mineable, that are for whatever reason quite deep, you can inject CO2 and it will adsorb onto the coal and displace methane, and so you might bring up some coal bed methane in the process. But the place where most people are thinking who are looking at this issue is in deep saline aquifers. So these are formations far below the drinking water level that is basically salty water that doesn't ever circulate with the human hydrologic cycle. And there's vast quantities of that kind of capacity, these sedimentary formations, all around the world. And that's viewed as the most likely long-term place for storing CO2. And so this is a map that shows the sort of based on the understanding of the geology in these different regions, the expectation of where you can put CO2, and the most likely places are in these deep orange colors. So you see the United States and Canada has quite a large potential there. Some in the Middle East here, some here, some in Russia, a little bit off the coast of Brazil here. But then there's also places where there might be, we don't know, we need to explore a little bit more. There might be pretty good places to put it, places like Sub-Saharan Africa, Australia, Southeast Asia, and so on. So this was an early estimate, but it's getting refined over time. People are looking at specific regions much more carefully, and actually there are a number of projects now going on to store CO2. But of course, people are worried about leakage as well, and what you worry about is the CO2 not staying down and coming back to accelerate the climate change. You can also have CO2 that will sort of bubble up underground and asphyxiate plant growth. And you can also potentially get it leaking into shallow groundwater in different ways. And so there's a lot of people who are doing research to try to understand these different leakage pathways. You have a question?
Is there a business model for this besides the carbon market? Who is paying for the capture and storage?
There is no business model other than the carbon market, except for the enhanced oil recovery, which there is you get paid for, yeah. So, but that comes back to the first question that you had was, what is the value that people are putting on avoiding carbon, right? And right now, there is no market for this. But there's work to understand. I won't go into too much detail, but there's a big research program at Princeton and other universities where they're trying to test to understand how things are going to leak, if they're going to leak, and to figure out how to address those, and that's an important area of research. But if you look at it sort of from first principles, what keeps the CO2 underground is the following. So this is stylized view of what the subsurface looks like. You'll have different layers of different kinds of stone, shale and sandstone and so on. And shale is a very non-porous rock, which is actually, you've heard of hydraulic fracturing for natural gas production. They break up this shale in order to produce natural gas, but if you don't break it up, it's quite a solid seal, and so you have a very porous formation underneath what's called a cap rock, and that's the primary way that the CO2 stays underground. But then there are secondary mechanisms for keeping the CO2 below ground. One is called capillary forces or residual trapping, and if you look sort of microscopically at what's going on within the within this layer down here, you'll see water, you'll see CO2, and you'll see rock. And the CO2 gets into spaces where the capillary forces keep it from flowing out. So that's not sure why it's going on its own. So that's one of the secondary mechanisms. And then you can also get CO2 dissolving into the water, the salty water. And then finally you get conversion into carbonates or solid materials. And so these are secondary mechanisms, but the primary one is this cap rock sealing. And if you look over time, what happens is that when you first inject CO2, the main mechanism for trapping is this cap rock. But over time, you get more residual trapping, you get more solubility trapping, and finally you get more mineral trapping in a very long time frame. So as the longer you go without leaking CO2, the more likely it is to stay down. So we're still developing a lot of understanding about this whole process, but it's starting to be recognized enough that there are a number of real projects going on around the world. There's an organization that's based in Australia that keeps track of all the projects going around the world, and I've listed just a few here to give you an idea of what the activity is around the world. So the very first project that was, and I'm not going to talk about all of these, just some of them, but the very first project that with CO2 capture and storage was injection into a saline aquifer, one of these deep formations. And they've been putting about 1 million tons per year of CO2 for over 20 years below the bed of the North Sea. This is a project called Sleipner, where they are extracting natural gas that is a mixture of natural gas and CO2. They strip the CO2 out, they send the natural gas to the Norwegian market, and the CO2 goes down below ground. And that's been 20 years that they've been injecting and monitoring it quite carefully. Question?
Please, can you go back one slide, please, 1 or 2, or another, please. I think it's 1 or 2. Is it the map of the potential? This one, the next one. I just thinking about how you measure this highly prospective. It's about the permeability of the rocks. It's about how you can measure this potential, the potential of the whole world. And these colors have some relation with the next slide about the primary and secondary. I forgot another word.
Yeah. Secondary mechanisms. No. So this slide doesn't have a connection to the trapping mechanisms. This was done solely on the basis of what the understanding of the geology. So you want to have a porous formation that is deep underneath an impervious formation, right? So, and if you're a geologist and know the way geology evolved over the Earth, you know that certain areas in the Earth will have the same kind of geology. So that's the basis for making this estimate. It's not, ultimately you have to drill wells and do those kinds of measurements to determine whether it's really feasible or not. But the expectation is you would, if you started testing in this area, you would be more likely to find a suitable formation. Does that answer the question? Yeah. Okay, I talked about this one because that's the very first one that, first project of large scale, 1 million tons per year of CO2, and has been quite successful, carefully monitored because it was the first of its kind. Another one that has been running, these two here, well, let's go to this one, US, Canada. This is a synfuels production from coal, which is in North Dakota in the United States. This was a project that began in the oil crisis in the late 1970s, and it has continued to make transportation fuels from coal, but capturing CO2 and sending it into across the border to Canada, where it's being injected for enhanced oil recovery. And they've been running for about 8 years now, putting 3 million tons per year of CO2 into, and again, being monitored very carefully because it was an experiment in CO2 storage. There are a number of other ones. The other one I'll talk about here. Yes, sorry. EOR, enhanced oil recovery. So putting CO2 into the oil well and getting more oil out. Yeah. This one right here is just started last year. Again, 1 million tons of CO2. That's coming from a corn ethanol plant. So that's the first, I would say, the first real BECCS plant that's operating in the world. This is taking the CO2 from the fermenter. It's a very pure stream of CO2, quite inexpensive to capture. You compress it, and it happens that Illinois overlays a very large formation, geologic formations that's ideal for CO2 storage. It's called the Mount Simon Aquifer. So the point here is that there are a number of projects where we're trying this out, and there is no real market driver, except in the cases for EOR, you get paid something for your CO2, but even that is not, probably doesn't justify the cost of these projects, so there's often government support that goes to help. Here's the Norwegian one. So this is a gas field, natural gas. So they drill through to take natural gas up. Right here on the platform, they separate the CO2 chemically from the methane. The methane goes to the continent, and the CO2 goes down and is injected in a separate formation. So it's actually, the formation here is actually higher than the one down here. But this one they've monitored very carefully. This is the injection point, and these are mappings of the CO2 that's been moving under the ground. So they're learning a lot through this process, and so far it seems to have been quite successful.
Thank you. How do they do the separation of methane and CO2?
It's some kind of an amine separation of, yeah, like a chemical adsorption process. I'm not sure the exact, yeah. And this is the ethanol fermentation CO2 in Archer Daniels Midland corn ethanol plant in Decatur, Illinois. They finished a 3-year trial in which they injected a total of 1 million tons over the 3 years, and they're now started just last year injecting 1 million tons per year. And this is a schematic of the way they do this. So you have CO2 coming out and goes through some kind of a purifier. It doesn't need much purification, but then you compress it and you put it underground. All right? So it's in this case, the ethanol is probably the best source of CO2 because it's already concentrated compared to say a flue gas from a boiler. I think I'll skip the EOR, except to say that in the United States, these blue lines here, these are CO2 pipelines that are already in existence. And it's unfortunate, but natural CO2 is extracted from the ground and piped 800 miles into Texas from Colorado to use for enhanced oil recovery. So they're actually mining CO2 rather than capturing it from sources because it's a lot cheaper to do that. But the point here is that you have a lot of pipelines that that are carrying CO2 around today. All right, so that's CO2 capture. We understand how to do it, the economics. There's not a market that drives it right now, but we have sort of the tools in the toolbox if we need to use them. So that leads us to bioenergy with CO2 capture and storage. This is a cartoon of the carbon flows that would be involved. So here we're growing biomass. So photosynthesis is taking carbon out of the atmosphere, and we take the biomass to some kind of a production facility. Some of that carbon is going to get stored in the roots and soils. There's some emissions that come from machinery that we might use for cultivation and harvesting. And then at the facility, we capture some CO2, and that goes into storage. We might have a char byproduct and use that to store. We'll also we can't capture all of the CO2, so we might emit some CO2 here. And then we might generate electricity from that overall process. And if you draw a line across here to the atmosphere, you can see that and these arrows are more or less to scale, there's more carbon coming out of the atmosphere than going back into the atmosphere. So on a life cycle basis, and we're assuming that this biomass is being grown every year. If we also make fuel, or make fuel instead of electricity, now some of the carbon goes with the fuel, and we burn it in airplanes or cars or what have you, and so we have some more emissions to the atmosphere. But again, if we draw a line here, we'll still have more coming out of the atmosphere than going into the atmosphere, and so it's net negative emissions. So that's the carbon balance for a BECCS system. And most, as I said at the beginning, most of these 2 degree C scenarios, whoops, I have a question back here. Oh, you got it.
Thank you. When you speak about EOR, you are referring enhanced oil recovery? How could be a CO2 method, a sequestering method like this, and so efficiently if the EOR method is used for recover oil that eventually is going to end in more CO2 emissions?
Excellent question. I was waiting for somebody to ask that. So if, let me ask you a question. Is the amount of oil that we consume in the world, does that change if we start a new oil well? Sorry. So the demand for oil is determined by other factors, okay, by what the price is, what cars people are driving, and so on. So if we add more oil to the global oil quantity through an EOR practice, somewhere else there's going to be less oil consumed because there isn't a demand for it. So that's the argument in today's world. As we get to a world where we're using very little oil, then the EOR, you're absolutely right that the EOR is going to be adding more. But in general, the demand for oil sets how much oil gets consumed, not how much we produce by EOR. So that's the argument. Okay, so as I said in the beginning, these 2 degrees C scenarios tend to want negative emissions. And I didn't tell you how they get negative emissions, but they tend to love BECCS technologies for achieving negative emissions. And in most cases, they are dealing with electricity generation systems. And in this case, it's a gasification system, CO2 removal, and then a combined cycle to make electricity. That's a technology that I spent a lot of years trying to understand. And it hasn't developed quite to commercialization, but you could also have a conventional Rankine cycle system here, a little bit less efficient. Or you could have liquid fuels as well with carbon capture and storage. This is Fischer-Tropsch system that I showed this morning. I won't go into the details, but basically you can capture CO2 and make electricity, or you can capture CO2 while you're making liquid fuels. And the reason that, so this is just a busy graph, but these are all different scenarios that were run in these climate models that said that we need BECCS. And the message here is that there's these deep decarbonization scenarios, these 2-degree scenarios, they love BECCS. That's the technology that they choose. And the reason for it is quite simple. So this is showing the cost of generating electricity with different technologies. So this is levelized cost of electricity in dollars per megawatt hour as a function of the greenhouse gas emissions price. So the way these models in the IPCC, the way they get lower and lower emissions is by cranking up the price that's charged for CO2 emissions. So the higher the price of CO2 emissions, the less CO2 gets emitted. And you keep cranking the price up until you reach the whatever target you're looking to reach, like 2 degrees C, for example. And so what I've shown here is what it costs to make electricity from a coal-fired power plant as a function of the greenhouse gas price, and then also from a natural gas combined cycle as a function of the greenhouse gas price, right? So this line is steeper than this line because coal electricity per unit of electricity produces more CO2 than a unit of natural gas electricity, all right? Now you can put this, these are both without CCS. You can add carbon capture to this technology. So if you add it with coal, your cost, even with no carbon price, goes up because you have to pay for the capture. But then as you go to a higher carbon price, your slope of this line is less steep than this one because you're capturing the CO2 and not emitting so much, right? So if you have a carbon price about $80 a ton, then it looks like it would be economical to put CCS on a coal-fired power plant. Similarly, with natural gas, the same kind of picture, but the crossover now is about $100 per ton of CO2. So where does BECCS fall on this kind of a graph? So that's BECCS. Because you're taking CO2 out of the atmosphere, you're actually getting paid for your negative emissions. So that offsets your costs of production. So what your net cost of production is coming down as the CO2 price goes up. And if you go, I didn't show the 0 point on here because it's very high, right? So if you're doing BECCS but don't have any carbon price, it's $300 a megawatt hour or something. It's a very expensive way to make electricity. But if you want to get to a 2 degree C world, you need carbon prices above $100 a ton. And so the BECCS looks very attractive, and that's why the models all say we need a lot of BECCS. It doesn't have anything to do with the technology's ready or if it'll work or anything. It's a model exercise. But this is the reason that so much attention has come to BECCS, is basically in this graph here. So how much BECCS are we really talking about? Okay, so I showed you this earlier. So let's assume that these negative emissions down here, let's assume that we want to provide those all with BECCS, which is basically what the models assume. We can do some pretty easy calculations from here. This is emissions of CO2 per year, and this is a 2 degree C scenario. And if we convert the amount of BECCS that's assumed in that scenario, so this is the generating capacity in gigawatts of electric generating capacity over time, and it's just taking these negative emissions and turning them into electricity generation given how much CO2 you can capture for each unit of electricity generation. And you can see that this is the rate at which you would have to add BECCS generating capacity. From 2030 to 2050, we need to build over 200 plants per year, 38 gigawatts per year. It slows down a little bit and then speeds up again as we get further out. And just for comparison, a technology that we know very well, coal-fired power plants, the average rate of addition of new coal-fired power plants is about 60 gigawatts. So these numbers are not unreasonable in terms of if we know the technology and know how to deploy it. These units don't have any CCS. They're just standard technology that's 100 years old. We know how to do it. So there's some question of whether we can go at this kind of a rate. Another way to look at these numbers is how much CO2 do we have to put below ground, okay? And what I'm going to compare it to here is so this is what BECS requires for global CO2 storage relative to the amount of oil production that was going on globally in 2015. So if you imagine oil coming out of the ground, you want to reverse that and put a fluid below ground. So by 2040, 12 years' time, we have an industry that's putting CO2, the same amount of CO2 below ground as oil coming out on a volume basis today. So if you can imagine an industry, the oil industry being built in 12 years, then you can believe these model results, right? Does that make sense? So these models are basically ludicrous in terms of the projections that they're making. But at the same time, it's drawn the whole world's attention to BECS, and people start thinking we'll solve the problem by doing this. It's not nearly as simple as that. On top of that, you need to have the biomass to provide for these systems, and these are just a range of estimates of how many exajoules a year of sustainable biomass we can get. I think this is in 2050. And you can see it's anywhere from 0 to more than 600 exajoules. And I didn't do the calculation of how much biomass we'd be using in those BECS. It's somewhere in the 100 to 300 range, I think. So there's questions, all sorts of questions about the feasibility of BECS, okay? This was a recent analysis of those same scenarios that was done to see how fast they're assuming you're changing the land use in order to meet the BECS requirements. So this historical rate of increase of soybean and oil palm, so this is the relative rate of expansion in percent per year. So, you know, in some years soybeans expanded more than 10% per year, but then kind of fluctuated. Sort of on average it's maybe 7 or 8% per year. And then these are the scenarios of energy crop expansion in these 2°C scenarios. So they're assuming that you're getting very rapid change in land use, and you're using a lot of land, half a billion hectares of land for energy crops. So again, lots of assumptions that don't come out when you see these results, but they raise a lot of questions about BECS. Well, and then I'll just leave with a question, you know, what if emissions don't peak until 2030, which is, so all of these scenarios have been here, right? Then if we don't peak emissions until 2030 and then start to bring it down, we need that much more negative emissions. And I actually did the calculations, and we basically need twice as much BECS as I was talking about here if we don't peak until 2030. So I hope I've made you a little bit skeptical about BECS on the scale that we're talking about here. I think it's still an important area, and negative emissions are going to be important, but we can't get carried away with having found a solution to the climate problem because we think that BECS is going to do it. All right, so, yes?
Just to raise the controversy, IEA Bioenergy, the director, I can't remember his name now, of course, they claim that this is the only solution. I was paying attention to their presentation in last Bonn Climate Conference, and they presented BECS as the main solution for climate change. Who knows? So
main solution with what temperature rise? 2 degrees C? Yeah, I don't think that's going to happen. I think we're going to need lots of different things to get there. And I think first and foremost is going to be energy efficiency and reducing the amount of energy that we use. Question, comment?
Yeah, I'm so thankful for you for this presentation. I think it's really eye-opening and very well put. And actually, you presented the answer to my question. My question was whether or not the cheapest form of carbon capture is not to get the oil or the gas out of the... Could you go back, please, to the chart that shows the economics comparison where the green line is steeply declining? Because there is an intersection with the natural gas, the blue dotted line. Yeah, that's the price, exactly. So what price is that? $7.80 US a megawatt hour? If you put that $80 US, no, I'm looking at the other axis, yeah, the x-axis. That's the price, right? There's a levelized cost of electricity. It puts at $80 US. Can we or not generate renewable energy without any emissions by solar or wind at $80 US megawatt hour? I think we can much cheaper. So neither BECCS nor fossil will need to be used. Is it or not?
Does the wind blow all the time? Does this? Yes, of course, the storage, which is not in the... So wind is maybe $70 a megawatt hour. Solar is higher than that right now, but neither of those are continuous. So you add storage costs on top of that, and you'll be above these numbers. We can yeah. We can debate probably for a long time, but yeah. But I think my bottom line is that we're going to need everything, okay? And there's not one thing that's going to solve all the problems. So we have enough creative people and enough young people who are interested in these problems and you guys are going to solve this for us because I'm not going to be around that much longer. So but I think I had one more slide just to sum up. Okay. All right, so we said that the remaining carbon budget is a big number, 600 to 1,200, and there's a big difference in those numbers, but there's a lot of uncertainty about it. But either one of them is small compared to the amount of fossil carbon that we still have left. And I believe that negative emissions, if we want to meet this, sooner or later we're going to need that. And the models that deploy BECCS widely and cost effectively, it's because of the costs that they assume for that. And as I showed this morning, the costs of technologies, second generation biomass technologies are very uncertain. And I suspect that the numbers that were used are probably on the optimistic side in this analysis, which would change the results quite dramatically. And so I asked the question, when will costs of sustainable BECCS reach levels assumed in the models? So I'll leave you with that question. So if we don't have really aggressive technology development, research and development, and new ways of regulating bioenergy and CO2 storage, there's no way we're going to have technology available to be deployed as soon as 2030 on a widespread basis the way the models want. So some of the questions that we have to worry about are, how should, when you're talking about a large biofuel industry, and I think Brazil maybe has faced a lot of these issues on a scale of the Brazilian ethanol program, but if we're talking about globally, it's that much more complicated. But how should we regulate biomass supplies so that they provide to avoid negative impacts on food, water, and ecosystems? I didn't talk about it, but there's something called the mountain of death for technologies, where when you first come up with a technology idea, it seems like the greatest thing since sliced bread, and it's so cheap, it's going to be just save the world. And as you work your way developing the technology. It keeps getting more and more expensive until finally you get some commercial deployment, and then the costs start to come down. So this thing is called the mountain of death because most technologies don't make it over that mountain of death, and somebody has to pay that. And in the case of Brazil, the ethanol industry, I think, faced that, and they made the decision to get over that mountain, and they did, and the costs have come down. But that's the kind of mountain of death we're facing with a lot of these BECCS technologies. And then there's also the CO2 storage. It costs a lot of money to figure out where that CO2 is going to go. You have to drill wells, you have to do all sorts of measurements, and you have to do them in many different places. Somebody's going to have to pay for that. So looking ahead, just some ideas for maybe ways to get ahead. There's a public-private partnerships are going to be important for supporting R&D because the private sector has the potential to benefit with new technology if they can develop it and the market is created for it. There's an organization called the Breakthrough Energy Coalition. Has anybody heard of that? This is Bill Gates, Microsoft CEO. He and a bunch of other billionaires said that they would create a fund if governments around the world would match it. And so it's several $1 billion of funding to try to develop technologies for dealing with the climate challenge. And this was announced at the Paris Agreement. There has to be sharing of information and technology across countries because these systems are too expensive for any single country to take on. And there has to be work on other negative emissions options in addition to BECCS because we don't know which is going to win in the end. And then we need carbon mitigation policies to really drive these kinds of systems and deployments, especially if we want to start as early as 2030. So there's a lot of challenges outside of the technical realm, but there's also a lot of R&D that has to happen on these kinds of technologies. And I guess you folks are working on some of the ideas that are probably going to play a role in the longer term. So that's, I think, all I had. Oops. Yep, that's it. So thank you. Questions?
Hi, I'm Pedro from Portugal, and I got a question. When we usually produce biofuels, we locate these crops outside of our cities, of course, but the main pollution will come inside of the city. So which of these carbon capture techniques will play a big role in decreasing these pollution centers?
Well, so usually the carbon capture technologies will be, CO2 is sort of the last pollutant that gets captured. You have to take other pollutants out before you get to the CO2 capture, otherwise the CO2 capture won't work. So are you asking about the pollution from biofuel facilities? Or?
Yes, but other types of pollution as well, because we are trying to tackle this CO2 emissions issue, right? And so carbon capture can be a way to decrease emissions in the near future.
So it's, yeah.
So, excuse me. So what I was asking is, we have like the two negative emission types, the biologic and engineered, and maybe the direct air capture could be applied in the cities. How can we?
So the direct air capture is nice in that you can put it anywhere, essentially, but you do have to then collect the CO2 that's captured and take it to a storage site somewhere. So some of the companies, they're research companies that are working on direct air capture. They actually want to use the CO2 with electrolytically produced hydrogen to make a fuel like methanol, so that they don't have to do the CO2 storage. I think all of those, the economics of those kinds of ideas are very challenging right now. But in terms of capturing CO2 from more concentrated streams, like a combustion gases from a biomass-fired power plant, in order to do that capture, you have to first take out the more conventional pollutants. You have to capture them, otherwise the CO2 capture system won't work because of either the catalysts or the solvents will be contaminated. So if you're doing CO2 capture, that means you've already cleaned up the process quite thoroughly. Yeah. Any more questions? Or?
Hello. Thank you, Professor, for the really nice presentation. I was just wondering, do you know if there's any study that combines the biomass power plants with the carbon capture storage potential, like as if it was an atlas combining both? Because in the biomass power plants, you will need a specific kind of rock to inject this CO2. It will not be able to do it in any place that where you have a biomass plant.
I see. So yes. So in the U.S. at least, there's a carbon storage atlas. It's called, which has mapped out the places where the formations are particularly favorable for storage, and then in terms of where you put biomass plants, one could locate relative to that. Is that the question you were asking? Or?
Yeah, actually, I was thinking about already existing biomass power plants, so that you will implement the CCS.
Oh, I see, the existing ones. I haven't. So we just had a PhD thesis that finished where there was an investigation of the location of storage relative to the corn ethanol plants. Okay, so the corn ethanol plants, they all produce CO2, and it's very cheap to capture. And what would be the system that you would put in place if you wanted to do that capture, and where is the places where you would store it, and so on. So there's been some work done on that, yeah.
Perfect, thank you.
Thank you. I remember in the list of CCSE projects, there is one ethanol plant in Illinois, is that so? Where you capture CO2. You capture only from fermentation, or you capture only also from flue gas? Only fermentation. Okay. Flue gas is more difficult.
Much more difficult. So the fermentation CO2 is 99.9% pure. With combustion, it's maybe 10% CO2. So if you're a chemical engineer, so you know, So it's much harder to capture 10% than 99%, and it's much harder to capture 400 parts per million, which is direct air capture, than 10%.
Professor Larson. So Daniel, maybe you remember that we started a conversation a couple of days ago. So the thing is, okay, I agree with you in the part that there is a large potential in the capture of the CO2 by means of production of biofuels, in my case fertilizers, ammonia, and whatever, because it reduces effectively the net amount of CO2 in the atmosphere. The problem remains to be the capacity. So we were discussing that in my case, if I would like to be competitive with the plants, the scale of the plants that produce like 1,000 tons per day of ammonia, I need to use a gasifier that is at least 600 megawatts. So it will be like 3 times, or 3-fold, the largest one, that is the Vattenfall, 160. So the 160 megawatts, that is the largest one. So the thing is that you think that the high pressure technology will overcome these problems in terms of capacity, because that is one of the things they are discussing nowadays. They say, if you use entrained flow gasifiers at high pressure by using oxygen instead of air, you will obtain like a larger gasifier, but you will have to pressurize this biomass in the pharma slurry by using screws and whatever. And all those problems have not been addressed so far, and probably they are not going to be addressed in the near future. But you think that by using the low pressure gasifiers with air in a separated twin Battelle gasifier, for example, and catalyst, we can increase this rate of reactions by means of, I don't know, reducing the pressures and temperatures like it has been done in other type of biological processes. It's because this bottleneck of the capacity is the thing that doesn't allow the fertilizers production by means of renewables. That is, just for mentioning, for connecting all of this information, is because we are working in the production of fertilizers by integrating the pipelines of natural gas and trying to decarbonize this sector in Brazil by introducing biomass. Because the biomass plants, they produce like 190 tons, a million of tons of bagasse per year. And one plant of 2 million of tons per year will be able to feed all of the biomass that is required to produce 1,000 tons per day ammonia plant. But the capacity is, I mean, we will need like 3 of these plants. The economy of scale is lost. So what do you think that is the next step in order to tackle this problem? In the catalyzers, pressures, thicker reactors, or we definitely need to move to biological processes, whatever we are speaking in this.
Well, so maybe we'll talk about the details offline, but I think your economics assume no carbon price, right?
Well, we are working that, I don't know, the Professor Swanee, she mentioned that there is a mill that is selling this value. So we took a representative value in the world economy of the CO2, but it's really low. I mean, it's like 0.000 euros per kilogram. So we took into account this, also took into account the value of ammonia. So we are indeed profiting from the production, the capture, but the problem remains to be the capital cost. So we did the analysis, and the capture is indeed negative, is minus 2 point something kilograms of CO2 captured per kilogram of ammonia. Okay, so there is a gain there. Then the operational cost, by considering that the bagasse is 20, so it's $20 per ton, and it's too cheap. You compare it with the 3 times that if you buy like other type of wood for producing ammonia in Germany or in other Eastern European countries. So it's really cheap. The operational cost is cheap. The bagasse is already concentrated. You don't have to transport it. The thing is, how can we put these scales in the same scale of the gasification of coal, that is 2,000 megawatts, but in bagasse is 160. This is the, you understand the problem that we cannot.
Yeah, that's the challenge.
Yeah.
But let's talk about it offline, because I think it's, maybe we're going to get into too much detail that won't interest everybody here. So, but let's talk right after we close the session here.
Hi, my name is Flavio from Ghana. I'm just curious about something. You know, we have biogas upgrading. Yeah, so can we classify biogas upgrading under CO2 capture?
So when you upgrade the biogas, it's maybe 50% CO2, and you take that away, right? So sure, clearly you've captured it, but the quantity is probably quite small. And so when you start thinking about what you do with that CO2, if you're going to put it in a pipeline to take it somewhere, that's going to be very expensive. If you can have a local market for it, you know, for a greenhouse or something, that might be a better option. But I think the scale is quite different than what I'm talking about here. Yeah.
All right, thank you.
Any more?
Really being very interesting point to this, the CO2 problem. I'm wondering the question of the scenario you worked with for the CO2 for the BECS because you probably set up some ideas that because you have to couple with this, the energy consumption in the world in the future. So the other technologies probably will be emitting more or less. We really don't know. There are some scenarios behind that, right? You probably froze that scenario now or assume some technology path, I don't know, for the world, because there are many technologies going around that also wants to decrease the production of CO2.
No, so for the scenarios, I just took the IPCC emissions trajectory, which they determined by looking at lots of different technologies, and they included BECCS as one of those technologies. And so I just took what they said was going to happen with BECCS. Yeah. Okay, I think people are worn out now, so maybe should we stop here? Any more questions? Okay. Class dismissed.